There's something deeply human about staring up at the night sky and wondering what lies beyond. For centuries, we've been drawn to the stars, not just as distant points of light, but as destinations, places we might one day reach, explore, or even call home. That restless curiosity has driven us to achieve the impossible, from launching the first satellites to planting footprints on the moon. But what if I told you we're standing on the brink of an even greater era? A time when 20 groundbreaking space missions could reshape everything we know about our place in the universe. Picture this: probes venturing into the icy oceans of distant moons, hunting for signs of life. Colonies rising on Mars, not as science fiction, but as bustling human settlements. Telescopes so powerful they could uncover the secrets of dark matter or spot Earth like planets light years away. These aren't just dreams, they're missions already in motion, each one a stepping stone toward a future where the cosmos becomes our backyard. And today, we're diving into the most ambitious, awe-inspiring projects that could redefine humanity's destiny. Some of these missions will push the limits of technology, while others challenge our very understanding of life itself. Think about it. What if we discovered another living world? What if we unlocked the keys to interstellar travel? The possibilities are as vast as space itself, and every breakthrough brings us closer to answers. So whether you're a lifelong space enthusiast or just someone who's ever looked up and felt that spark of wonder, this journey is for you. Buckle up, we're about to explore the 20 missions that could change everything. Let's start with a pair of trailblazers that have already rewritten the history books: Voyager 1 and Voyager 2. Launched back in 1977, these twin spacecraft were originally designed to study Jupiter and Saturn, but they've long outlived their initial mission. Today, they're humanity's farthest flung ambassadors, hurtling through the void of interstellar space, where no human-made object has ever gone before. Think about that for a second. These machines, built with technology older than the internet, are now navigating the unexplored frontier beyond our sun's influence. What makes their journey so extraordinary isn't just the distance they've covered, but the secrets they're still sending back. Even now, decades after launch, Voyager 1 beams data about cosmic rays and magnetic fields from regions no other probe can reach. It's like getting postcards from the edge of known space. And then there's the golden record. Each spacecraft carries a time capsule of Earth sounds, music, and greetings in 55 languages, just in case another civilization ever finds them. It's a message of hope, a snapshot of who we were in the late 20th century, floating among the stars. But here's the real kicker: Voyager's work is far from over. As they drift deeper into interstellar space, they could uncover clues about the mysterious medium between stars, or even detect anomalies that challenge our understanding of physics. Their power sources will eventually fade, likely by 2025, but their silent journey will continue for millennia. They might outlast humanity itself, carrying our story into the cosmic dark. It's humbling to realize that long after we're gone, these tiny explorers could still be sailing onward, the last echoes of a species that dared to reach beyond its own sky. While the Voyagers carried our dreams into the interstellar void, another mission is peering even deeper into the cosmos, unlocking secrets hidden since the dawn of time itself. The James Webb Space Telescope isn't just another observatory, it's a time machine. With its massive golden mirror and cutting-edge infrared eyes, Webb sees what no telescope before it could: the faint glow of the universe's first galaxies, the chemical fingerprints of distant exoplanet atmospheres, even the building blocks of life scattered across the cosmos. And what it's already revealing is rewriting astronomy textbooks. Take those breathtaking early images, the towering, cosmic cliffs of the Carina Nebula, where stars are born in chaotic clouds of gas, or the ghostly light of galaxies so ancient their light has traveled over 13 billion years to reach us. But Webb's real power lies in the details invisible to our eyes. Its infrared vision pierces through cosmic dust, uncovering nurseries where planets form around young stars. It spies molecules like water vapor and methane swirling in alien atmospheres, hinting at worlds where conditions might support life. One recent discovery found carbon dioxide on a gas giant 700 light-years away, marking the first definitive detection of this molecule outside our solar system. Then there's the hunt for cosmic origins. Webb's gaze stretches back to an era when the universe was a toddler, just a few 100 million years old. Those faint smudges of early galaxies, they're smaller, weirder, and more chaotic than theorists predicted, forcing scientists to rethink how structure emerged from the primordial soup of the Big Bang. And the telescope's work is only accelerating. Up next, probing the atmospheres of rocky exoplanets in habitable zones, studying mysterious, dark stars that might be powered by exotic particles, even unraveling the enigma of dark energy. Every new observation peels back another layer of the universe's grand story. What makes Webb so revolutionary isn't just its tech, it's how it transforms abstract questions into tangible data. When it analyzes starlight filtering through an exoplanet's air, that's not just numbers on a screen. It's the closest we've come to sniffing the breeze of another world. And with at least a decade of operations ahead, Webb promises discoveries we can't even imagine yet. It's like we've been reading the universe by candlelight and someone just flipped on a floodlight. The cosmos has never looked so alive, so strange, or so full of possibility. While the James Webb Space Telescope expands our view of the cosmos, NASA's Artemis program brings our cosmic ambitions closer to home by returning humans to the moon, not just as visitors, but as pioneers building a lasting presence. This isn't a repeat of Apollo. Artemis is a blueprint for something far grander. Picture astronauts stepping onto the lunar surface as early as 2026. But this time, they're laying the groundwork for a future where lunar outposts become hubs for science, industry, and even springboards to Mars. The backbone of this vision is the Lunar Gateway, a cutting-edge space station that will orbit the moon like a cosmic waypoint. Unlike the International Space Station, Gateway isn't just a lab, it's a command center, a testing ground for deep space tech, and a safe house for astronauts venturing to the lunar surface. With modules contributed by international partners like Europe, Japan, and Canada, Gateway embodies global cooperation in space. One key innovation, its ability to operate autonomously, meaning astronauts can leave it unattended for months while they explore below. But the real game changer is sustainability. Artemis isn't about planting flags, it's about learning to live off the land. Missions will test technologies like extracting water ice from permanently shadowed craters, water that could become drinking supplies, radiation shielding, or even rocket fuel. Imagine a moon base powered by solar arrays with 3D printed habitats made from lunar soil. These aren't sci-fi fantasies. Prototypes are already being tested on Earth. And every lesson learned here directly applies to Mars. The moon's lower gravity makes it the perfect proving ground for systems that'll one day support human life on the red planet. International collaboration fuels Artemis's momentum. Beyond Gateway, NASA partnerships stretch from SpaceX's Starship lunar lander to ESA's Argonaut cargo delivery system. Even nations new to space exploration, like the UAE, are contributing rovers and research. This global effort mirrors the spirit of Apollo, but with a twist. Artemis aims to leave infrastructure that benefits all humanity, not just a single nation's legacy. What makes Artemis revolutionary isn't just the technology, it's the shift in mindset. We're not just going back, we're staying. And with each mission, from testing new spacesuits to deploying lunar GPS, we're rewriting the playbook for how humans explore space. The moon is no longer a destination, it's the first step in a journey that stretches to Mars and beyond. The clock is ticking, the next giant leap starts here. For every rock we've ever studied, every grain of sand analyzed under a microscope, they've all come from one place, Earth. But what if scientists could hold a piece of another world in their hands? That's the tantalizing goal of Mars Sample Return, arguably the most complex robotic space mission ever attempted. NASA and the European Space Agency have teamed up to achieve what sounds like science fiction, launching a rocket from the surface of Mars to deliver pristine Martian soil back to Earth. And the secrets locked in those samples could rewrite our understanding of life in the cosmos. The mission reads like a high-stakes interplanetary relay race. It began with the Perseverance rover, which has been scouring Jezero Crater, a dried-up river delta, collecting tube-sized samples of rock and soil that might preserve signs of ancient microbial life. But here's where it gets wild. Later this decade, a second spacecraft will land near Perseverance, carrying a miniature rocket and a fetch rover. That rover will race across Mars to collect the sample tubes, load them into the rocket, and launch them into Martian orbit. Meanwhile, a third spacecraft sent by ESA will intercept the samples in mid-flight and haul them back to Earth. The coordination is mind-boggling, like throwing a dart from Los Angeles and hitting a bullseye in Tokyo, only to have someone catch it midair. Why go to such extremes? Because labs on Earth have tools no rover could carry. Imagine slicing a Martian rock atom by atom with diamond knives, or bombarding it with particle beams to reveal its molecular secrets. Scientists could detect organic compounds at concentrations 1 billion times lower than any instrument on Mars. They might even find fossils of ancient microbes, proof that life isn't unique to Earth. Jezero Crater was chosen because 3.5 billion years ago it held a lake. On Earth, similar environments teem with microbial mats that leave behind layered structures called stromatolites. If Mars once had life, Jezero's rocks could hold its echoes, yet the challenges are staggering. Mars's thin atmosphere makes precision landings harder than on Earth. Dust storms could cripple solar-powered rovers. The samples must stay utterly uncontaminated. Any stray Earth microbes could masquerade as Martian life. And then there's the rocket launch. No spacecraft has ever blasted off from another planet's surface autonomously. The margin for error, zero. One glitch and decades of work vanish into the Martian dust. But the payoff would be astronomical. Beyond the search for life, these samples could reveal why Mars transformed from a warm, wet world into a frozen desert. They might hint at whether its resources could support future human colonies. And philosophically, they could answer a question that's haunted us for centuries: are we alone? For all its complexity, Mars Sample Return isn't just a mission, it's a time capsule from another world, and the key to unlocking one of humanity's oldest mysteries. Beneath the frozen crust of Jupiter's moon Europa lies an ocean not of ice, but of liquid water, stretching farther than all Earth's seas combined. It's a world encased in a shell of ice, cracked and scarred by tidal forces, hiding what might be the most promising habitat for life beyond our planet. That's why NASA Europa Clipper isn't just another spacecraft. It's a detective armed with a suite of instruments designed to answer one of humanity's biggest questions: could life thrive in the darkness of an alien ocean? Scheduled to launch in 2024, the Clipper won't land on Europa's surface. Instead, it'll perform a series of daring flybys, skimming as close as 16 miles above those frozen plains. Each pass is a high-stakes maneuver, threading the needle between Jupiter's crushing radiation belts and Europa's gravitational pull, but the risk is worth it. The spacecraft's 9 instruments will work in concert to map the Moon's subsurface ocean, measure its depth and salinity, even sniff out organic molecules in plumes of water vapor that occasionally erupt from the ice. One tool, an ice-penetrating radar, will slice through the crust like an X-ray, revealing hidden lakes or pockets of slush just beneath the surface. Another, a thermal imager, will hunt for hotspots where warmer ice might betray geologic activity below. Then there's the mass spectrometer, a device so sensitive it could detect the chemical fingerprints of life in a single grain of ice. If Europa's ocean contains hydrothermal vents like those on Earth's seafloor, where heat and minerals fuel entire ecosystems in perpetual darkness, their telltale molecules might seep through cracks in the ice and into space. The Clipper could catch them mid-flight. Even the Moon's bizarre surface features, from chaotic lenticulae domes to sprawling ridge systems, might hint at currents stirring the ocean below. Every crack and crevasse is a potential window into a hidden world. What makes this mission so groundbreaking isn't just the science, it's the sheer audacity of exploring an ocean without touching it. Imagine studying Earth's seas by only analyzing evaporating droplets in the air. Yet that's the challenge the Clipper faces. Its findings could redefine the boundaries of habitability, proving that life doesn't need sunlight or a warm planet, just liquid water, energy, and the right chemistry. And if it finds even hints of biological activity, Europa would leap to the top of the list for future missions, perhaps even a lander equipped to melt through the ice. The clock is ticking. With each flyby, the Clipper will peel back layers of mystery, turning speculative science into hard data. Europa's ocean has been sealed away for billions of years, a time capsule from the solar system's youth. Soon we might finally glimpse what or who is waiting in the dark. Saturn's moon Titan isn't just another frozen rock. It's a swirling, organic, rich world with rivers of methane cutting through dunes of hydrocarbon sand, where the sky rains gasoline and the lakes are made of liquefied natural gas. It's the only place besides Earth with stable liquid on its surface, and NASA's Dragonfly mission is about to take us there in ways we've never explored before. This isn't a rover or a lander, it's a nuclear-powered drone, a rotorcraft designed to hop across Titan's alien landscape, sampling its chemistry and hunting for clues to how life might arise in the most unexpected places. Dragonfly's design is as audacious as Titan itself. Imagine a helicopter the size of a small car, powered by a plutonium-fueled generator, flying through an atmosphere 4 times thicker than Earth. That extra density is the key. It gives the rotors enough bite to lift off effortlessly, allowing Dragonfly to cover dozens of miles between sites, far beyond what any rover could manage. Its first stop, the hauntingly familiar Selk crater, where ancient water once mixed with complex organic molecules, possibly creating the perfect conditions for prebiotic chemistry, the building blocks of life. But why Titan? Because it's a frozen time capsule of early Earth, but with a twist. Beneath its icy crust lies a subsurface ocean, but above ground, the moon is drenched in carbon-rich compounds like methane and ethane. Sunlight breaks these molecules apart, forming smog-like hazes that rain down and accumulate into dunes. In labs on Earth, simulating these conditions has produced amino acids, the same molecules that form proteins in living things. Dragonfly's instruments will do that science in real time, drilling into Titan's surface and baking samples to identify the organic soup hiding there. The mission's real magic lies in its mobility. After landing near Selk crater, Dragonfly will spend 2.5 years leaping from one compelling site to another, analyzing the surface with a suite of tools. A mass spectrometer will sniff out complex molecules. A gamma-ray spectrometer will map the elemental composition of the ground. Cameras will capture panoramic views of Titan's eerie, orange-hazed horizons, a landscape no human eye has ever seen up close. Each hop is a chance to compare different environments, from dried-up lake beds to icy plains, piecing together how organic chemistry evolves across this alien world. What makes Dragonfly revolutionary isn't just the science, it's the way it reframes our search for life. We've long focused on water as life's sole requirement, but Titan challenges that assumption. Could life emerge in methane lakes instead of water? Could cell membranes form from hydrocarbons rather than lipids? Dragonfly won't find living organisms, but it could uncover chemistry so familiar yet alien that it forces us to rewrite the rules of biology. If probiotic molecules are actively forming on Titan today, it would mean the universe is cooking up the ingredients for life everywhere, even in the most hostile corners of the solar system. The implications stretch far beyond Saturn. If Titan's chemistry mirrors early Earth's, studying its dunes and lakes could teach us how life sparked here billions of years ago. And if we discover entirely new pathways for complex molecules to assemble, we might finally understand whether life is a cosmic fluke or an inevitability. Dragonfly isn't just exploring a moon, it's probing the deepest question of all: how does matter become biology? By the time its rotors fall silent, we may have an answer. Now let's talk about a mission that sounds like it leaped straight from the pages of science fiction. Breakthrough Starship, an ambitious plan to send tiny spacecraft to our nearest stellar neighbor, Alpha Centauri, at a blistering fraction of the speed of light. This isn't about building a traditional rocket or a massive probe. Instead, the vision hinges on wafer-thin nanocraft, each no larger than a postage stamp, propelled by an array of powerful Earth-based lasers. The goal: to reach a star system 4.37 light-years away in just 20 years, a journey that would take today's fastest spacecraft tens of thousands of years. At the heart of Starship's design is an ingenious twist on propulsion. Picture this: a ground-based laser array spanning nearly a square mile, firing a concentrated beam of light at a fleet of nanocraft equipped with lightweight light sails. These sails, thinner than a human hair, catch the laser's momentum, accelerating the tiny probes to an unimaginable 20% the speed of light, about 134 million miles per hour. At that velocity, a flyby of Alpha Centauri's planets could snap images, collect data, and beam it all back to Earth in a little over 4 years. But the challenges are as staggering as the ambition. The laser system would require 100 gigawatts of power, roughly the output of 100 nuclear reactors delivered in minutes. The nanocraft must survive decades of travel through interstellar space, dodging cosmic dust particles that, at such speeds, could hit with the force of a bullet. Even the slightest misalignment in the laser beam could send the probes veering off into the void. And then there's the question of how to receive data across light years with a transmitter no bigger than a smartphone. Why take such a risk? Because the payoff could redefine our understanding of neighboring star systems. Alpha Centauri isn't just a pinprick of light. It's a trio of stars, with Proxima Centauri hosting a rocky planet in the habitable zone. Starship's flyby might reveal whether that world has oceans, atmospheres, or even surface features hinting at geology or biology. Even a blurry image of an exoplanet's cloud patterns would revolutionize astronomy. The project, funded by billionaire Yuri Milner and backed by legends like Stephen Hawking, is still in its infancy. Current prototypes are testing light sail materials and miniaturized electronics. If successful, Starship could launch by the mid-21st century. It's a high-stakes gamble, but one that could finally answer whether we're alone in the cosmic neighborhood or if another Earth has been waiting next door all along. Floating in a unique halo orbit around the Moon, the Lunar Gateway isn't just another space station. It's a cosmic pit stop designed to revolutionize how we explore deep space. Think of it as a combination of a research lab, a fuel depot, and a launch pad, all bundled into a modular outpost that will support missions to the lunar surface and beyond. Unlike the International Space Station, which circles Earth, Gateway operates in what's called a near-rectilinear halo orbit, a delicate gravitational dance that keeps it stable while offering prime access to the Moon's poles. This strategic position makes it the perfect staging ground for Artemis missions, future Mars expeditions, and even interstellar probes. What makes Gateway so groundbreaking is its modular design. The initial core will include two key components: the habitat and logistics outpost Halo, where astronauts will live and work, and the power and propulsion element PP, a solar electric powerhouse that keeps the station running. But the real magic happens with the additions. Europe is contributing the Esprit module, which will handle communications and refueling. Japan's building a state-of-the-art life support system. Canada's robotic arm, a successor to the one used on the ISS, will assemble new modules and assist with cargo. Even private companies like SpaceX are involved, delivering supplies via lunar-adapted Dragon capsules. The station's long-term goals read like a roadmap for interplanetary travel, one of its most critical roles, testing new technologies for surviving deep space. Gateway will experiment with closed-loop life support systems that recycle air and water with near-perfect efficiency, essential for Mars missions where resupply isn't an option. It'll also serve as a lab for studying how prolonged exposure to deep space radiation affects human biology, data we desperately need before sending crews beyond Earth's protective magnetic field. But perhaps its most visionary function is as a transportation hub. Future lunar landers will dock here, allowing crews to switch between vehicles optimized for different tasks. Need to ferry supplies down to a moon base? There's a lander for that. Preparing for a jaunt to Mars, Gateway could house the spacecraft that makes the journey. Some concepts even suggest it could host fuel depots where ice mined from the moon is processed into hydrogen and oxygen, the very propellants needed to power rockets. International cooperation fuels Gateway's potential, with NASA, ESA, JAXA, CSA, and other partners all contributing hardware and expertise. It's a model for how humanity might tackle the challenges of deep space together. This isn't just an American project, it's a global effort with each partner bringing specialized skills. Europe's expertise in modular spacecraft, check. Japan's precision robotics, double check. By pooling resources, we're building something no single nation could achieve alone. The station's phased construction ensures it evolves with our ambitions. Early missions will focus on supporting Artemis landings, but later expansions could include dedicated science modules or even tourist quarters. Imagine astronauts and private citizens alike gazing down at the moon's craters from Gateway's windows, all while preparing for humanity's next giant leap. This isn't just a space station, it's the first true stepping stone to the stars. Venus has long been the forgotten sister of our planetary neighborhood, a world of crushing pressures, scorching temperatures, and skies thick with sulfuric acid. But after decades of being overshadowed by Mars and the outer planets, Earth's evil twin is finally getting its moment in the spotlight. NASA Veritas and Da Vinci I+ missions represent a bold 1-2 punch of exploration, tackling Venus's mysteries from orbit and atmosphere with tools more advanced than anything we've sent before. Together, they're on a quest to answer a haunting question. How did this planet, so similar to Earth in size and origin, become the solar system's most terrifying hellscape? First up is Veritas, short for Venus Emissivity, radio science in SAR, topography, and spectroscopy. This orbiter is essentially giving Venus its first full body scan. Using a state-of-the-art radar system, it'll pierce through those perpetual clouds to map the surface in dazzling detail, down to features just a few meters across. Imagine seeing Venus's landscape with the same clarity we've had for Mars. But Veritas isn't just playing cartographer. Its infrared spectrometer will hunt for signs of recent volcanic activity by detecting heat signatures from potential lava flows. If it finds smoking guns literally, it could prove Venus isn't the geologically dead world we once assumed. Even more intriguing, the spacecraft will measure tiny variations in the planet's gravity field, potentially revealing whether Venus still has a churning, molten core like Earth's, or if it's cooled into stillness. Then there's Da Vinci I+, a mission that reads like something from a Jules Verne novel. While Veritas studies the surface from above, Da Vinci I+ will plunge straight into Venus's toxic atmosphere with a bullet-shaped descent probe. As it free falls for about an hour through clouds of sulfuric acid, this robotic daredevil will analyze the air's composition layer by layer, sniffing out noble gases like krypton and xenon chemical time capsules that could reveal how Venus lost its water billions of years ago. But the real showstopper comes in the final moments before the probe is crushed by Venus's 92 bar pressure, equivalent to being 3,000 feet underwater. A hardened camera will snap the first ever high-resolution photos of Venus's surface during descent, capturing a landscape no human eyes have seen directly since the Soviet Venera landers in the 1980s. What's reignited our fascination with this inferno? Partly, it's the rise of exoplanet science. Astronomers keep finding rocky worlds orbiting close to their stars, Venus-like candidates that might teach us about planetary evolution. But there's also a tantalizing hypothesis floating around. Venus may have been habitable for billions of years before a runaway greenhouse effect boiled its oceans away. Recent climate models suggest it could have had shallow seas and temperate weather as recently as 700 million years ago. If true, that means Venus and Earth were twin ocean worlds for most of the solar system's history, until something went catastrophically wrong on one. Understanding that tipping point isn't just about Venus, it's a warning for our own planet's future. The two missions complement each other perfectly. Verita's global maps will help scientists pinpoint where to search for ancient shorelines or mineral traces of long-lost water. Da Vinci+'s atmospheric data could reveal how much hydrogen and, by extension, water escaped into space over time. Together, they'll test whether Venus was ever a blue marble like Earth, and whether that means other Earth-sized exoplanets might hide similar fates beneath their clouds. After years of being dismissed as a dead end, Venus is now the ultimate planetary cautionary tale. These missions aren't just about rewriting textbooks, they're about uncovering whether hellish worlds are cosmic inevitabilities, or if Earth narrowly avoided becoming one. As the probes peel back Venus's toxic veil, we might find more than ancient geology. We might discover our own planet's reflection in its acidic clouds. Deep in the asteroid belt between Mars and Jupiter drifts a world unlike any other, a gleaming, metal-rich relic from the solar system's violent youth. Asteroid 16 Psyche isn't just another space rock. It's a cosmic time capsule believed to be the exposed core of a failed planet. NASA's mission to this bizarre object isn't merely about studying an asteroid. It's our first chance to examine what lies at the heart of rocky worlds like Earth without digging through thousands of miles of crust and mantle. What makes Psyche so special starts with its composition. While most asteroids are rocky or icy, radar observations suggest Psyche is almost entirely metal, iron and nickel mixed with rare metals like gold and platinum. Scientists suspect it's the stripped skeleton of a protoplanet that never finished forming, either because it collided with another massive object or had its outer layers blasted away by ancient cosmic violence. If true, this makes Psyche the equivalent of a planetary autopsy, offering us a hands-on look at the same building blocks that swirl in Earth's core today. The spacecraft, aptly named Psyche, is a technological marvel designed to unravel these mysteries. Scheduled to launch in 2023, it'll spend nearly 4 years cruising toward its target before slipping into orbit in 2026. Unlike missions that land or sample, this orbiter will map every inch of the asteroid from above using a suite of cutting-edge tools. A multispectral imager will photograph surface features in wavelengths far beyond human vision, while gamma-ray and neutron spectrometers will sniff out the exact cocktail of metals hiding below. But the real showstopper is the magnetometer, a device sensitive enough to detect whether Psyche still carries traces of an ancient magnetic field, the smoking gun that would confirm its identity as a planetary core. Understanding Psyche's magnetic history could rewrite planetary science. Earth's swirling liquid core generates our protective magnetic field, which shields us from deadly solar radiation. But how did that dynamo first start? How long does it last? Psyche's frozen magnetism might hold answers, preserving a snapshot of the processes that shaped our own planet's interior billions of years ago. There's even a chance we'll discover unexpected minerals or alloys formed under pressures impossible to replicate on Earth, materials that could revolutionize everything from industrial manufacturing to spacecraft design. Beyond pure science, the mission sparks practical questions. Could Psyche's metallic wealth someday fuel space industries? With enough platinum group metals to dwarf Earth reserves, this asteroid represents a trillion-dollar treasure chest. While mining it isn't the mission's goal, the data could inform future ventures, helping us understand how to extract resources from similar metal-rich bodies. It's a delicate balance, studying Psyche as both a scientific wonder and a potential resource node forces us to confront how exploration and exploitation might intersect in the coming space age. What makes this journey so profound isn't just the geology, it's the philosophical implications. Psyche offers a rare glimpse into the hidden engines that power habitable worlds. By studying this celestial wreckage, we're piecing together the chaotic processes that built not just our solar system, but potentially thousands of others. Every crater on its metallic surface tells a story of collisions and catastrophes, while its very existence hints at how many sibling planets might have failed to form. When the spacecraft finally beams back its first close-up images, we won't just be seeing an asteroid, we'll be staring into the mirror of Earth's own fiery origins. In the vast darkness between planets, cosmic vagabonds streak through our solar system, pristine comets and interstellar visitors carrying secrets from the farthest reaches of space. The European Space Agency's Comet Interceptor isn't just another mission. It's a high-stakes game of celestial hide and seek, designed to ambush one of these ancient travelers the moment it's spotted. What makes this mission revolutionary? Unlike previous comet chasers like Rosetta, which studied known targets for years, the interceptor is already parked in space, lying in wait for the perfect opportunity to pounce on an undiscovered object, possibly even a visitor from another star system. The mission's strategy is as bold as it is ingenious. Sometime in the next few years, the spacecraft will launch and slip into a unique gravitational parking orbit near the Sun-Earth Lagrange Point 2, a stable pocket of space about 1.5 million kilometers behind our planet. There, it'll remain dormant until astronomers spot a promising target, perhaps a long-period comet plunging inward from the Oort cloud for the first time, or even an interstellar oddity like Oumuamua or Borisov. Once a candidate is confirmed, the interceptor will spring into action, firing its thrusters to intercept the object at breakneck speed, the real magic. It actually carries 3 separate probes that'll split apart as they approach, each studying the target from different angles to create a comprehensive 3D profile of its structure, composition, and behavior. Why go to such lengths for a random comet? Because pristine comets are cosmic time capsules. Most we've studied, like Halley or Churyumov-Gerasimenko, have been altered by repeated trips near the Sun, their surfaces baked and eroded. But a first-time visitor, or better yet, an interstellar interloper, would offer an unspoiled sample of the raw materials that built the solar system 4.5 billion years ago. Imagine cracking open a geological textbook with pages untouched by time. The interceptor's spectrometers could detect organic molecules unchanged since their formation in interstellar clouds, compounds that might have seeded Earth with the building blocks of life. Its cameras could reveal whether these objects are rubble piles or solid chunks, settling debates about how planets form from cosmic dust. Then there's the tantalizing possibility of catching an interstellar object. The 2 we've spotted so far, Oumuamua's bizarre cigar shape and Borisov's comet-like tail, hint at an entire hidden population of cosmic nomads passing through our neighborhood. Studying one up close could reveal whether other star systems form planets the same way ours does, or if their chemistry produces entirely different minerals and ices. Some theorists even suggest such objects could carry microscopic life between stars, though the interceptor isn't equipped to test that radical idea. Still, the mere chance to scrutinize a piece of another solar system makes this mission a potential landmark in astronomy. The technical challenges are immense. The spacecraft might have just months or even weeks to reach its target after detection, requiring precision maneuvers worthy of a cosmic sniper. Its probes must operate autonomously, capturing data during a fleeting high-speed flyby with no second passes. And unlike missions with known destinations, the Interceptor's team must design instruments flexible enough to handle whatever bizarre features their target might spring on them: cryovolcanoes, weird outgassing patterns, or surface structures unlike anything in our solar system. Yet the gamble could pay off spectacularly. If successful, Comet Interceptor won't just add another chapter to comet science. It might rewrite the book on how small bodies shaped planetary evolution. Every molecule it identifies, every surface feature it maps, carries echoes of the cloud that birthed our sun. And if fortune smiles, it could give us front-row seats to something even rarer, a close encounter with a messenger from the stars. In the hunt for cosmic origins, this mission isn't just chasing comets, it's chasing ghosts of the solar system's birth, and perhaps even whispers from worlds beyond. For decades, space stations have been the exclusive domain of governments' massive projects requiring billions in funding and international cooperation. But a seismic shift is underway, led by companies like Axiom Space, which is pioneering the first fully commercial space station. This isn't just another orbiting lab. It's a vision for how low Earth orbit could transform into a thriving marketplace of research, manufacturing, and even tourism. And with its initial module set to dock with the International Space Station as early as 2026, Axiom's plan is closer to reality than most people realize. The station's design reflects a radical new approach. Instead of building a monolithic structure from scratch, Axiom is starting with a series of modular additions that'll attach directly to the ISS before eventually breaking free to form a standalone outpost. The first module, dubbed Axiom Hub 1, will feature state-of-the-art crew quarters with panoramic Earth viewing windows, a far cry from the utilitarian sleeping bag strapped to ISS walls. Next comes a research and manufacturing module equipped with facilities for microgravity experiments ranging from pharmaceutical crystal growth to advanced materials production. But the real game changer is the inflatable habitat module, leveraging technology pioneered by Bigelow Aerospace to create spacious, adaptable living areas that can be expanded after launch. What sets this venture apart isn't just the hardware, it's the business model. Axiom is betting on a future where access to space isn't limited to astronauts and elite researchers. Private companies could rent lab space by the week. Universities might send up student-designed experiments. Even individuals could book stays through space tourism packages, with prices expected to drop significantly as operations scale. This commercial approach could finally unlock the economic potential of microgravity, turning what was once a scientific frontier into a routine workplace. Imagine pharmaceutical firms growing perfect protein crystals for next-gen medications, or semiconductor companies producing defect-free alloys impossible to manufacture on Earth, all while paying customers float through observation lounges snapping photos of the auroras below. The station's potential extends beyond profit. By taking over low Earth orbit operations, Axiom could free up NASA and other agencies to focus on deep space exploration while maintaining a continuous human presence closer to home. The company has already trained private astronauts for ISS missions, proving the viability of its approach. Future plans include partnerships with national space agencies needing cost-effective access to orbit, potentially making the station a hub for global collaboration without the political complexities of the ISS. Yet challenges loom. The economics of commercial stations hinge on dramatically reducing launch costs, something SpaceX and other providers are tackling head-on. There's also the question of how multiple commercial stations might coexist without overcrowding orbital slots. And unlike government programs, Axiom must turn a profit, meaning every module must justify its existence through revenue streams ranging from research contracts to media deals. But if successful, Axiom Station could mark the beginning of a new era, one where space isn't just explored but lived in and worked in by everyday people. The implications ripple far beyond tourism. Artists could create in zero gravity, athletes might train in high-performance environments, and filmmakers could shoot sequences in true weightlessness. This isn't just about building a station, it's about proving that space can be more than a destination for the few. It can be a workplace, a laboratory, even a home for anyone bold enough to reach for it. While the James Webb Space Telescope has dazzled us with unprecedented views of the early universe, astronomers are already planning its successor, a revolutionary observatory that could deliver something even more profound: crisp, direct images of Earth like planets orbiting distant stars. Meet LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, a next-generation space telescope concept so powerful it might finally answer humanity's oldest question: are we alone in the cosmos? LUVOIR isn't just an incremental upgrade. Where Hubble revealed the beauty of the universe and Webb peered through cosmic dust to uncover its infancy, LUVOIR is engineered for one audacious goal: to spot pale blue dots around other suns. Its design reads like science fiction, a segmented mirror up to 15 meters across, nearly 6 times wider than Hubble's, equipped with coronagraphs so advanced they can blot out a star's glare to reveal orbiting planets a billion times fainter. Imagine seeing not just blobs of light, but actual disk cloud patterns, continents, even signs of vegetation on worlds light years away. The telescope's ultraviolet to infrared range makes it a universal detective. While Webb excels in infrared for studying ancient galaxies, LUVOIR's broader spectrum lets it hunt for biosignatures, atmospheric gases like oxygen, methane, or industrial pollutants that might betray alien life. Its spectrographs could analyze the reflected light of an exoplanet's oceans, searching for the telltale glint of liquid water. Some concepts even include a starshade, a giant sunflower-shaped screen that would fly 40,000 kilometers ahead to block starlight with pinpoint precision, unveiling planets hidden in their sun's glare. Comparing LUVOIR to its predecessors highlights its staggering ambition. Hubble's deep field images captured thousands of galaxies in a speck of sky. LUVOIR could resolve individual star clusters within those galaxies. Webb detects exoplanet atmospheres by studying how starlight filters through them during transits. LUVOIR would photograph those planets directly, tracking seasonal changes or city lights. Where current telescopes infer a planet's habitability from orbital calculations, LUVOIR might spot chlorophyll-like pigments or the spectral fingerprints of artificial greenhouse gases, evidence not just of life but of civilizations. The challenges are as immense as the potential. Building a mirror this large requires folding it like origami for launch, then deploying it flawlessly in space. The coronagraph technology demands stability so precise it could detect a vibration less than the width of an atom. And with an estimated price tag rivaling the Apollo program, LUVOIR would need unprecedented international funding. Yet early tests of its key technologies, including high-contrast imaging at NASA, a jet propulsion lab, have been promising enough that the National Academy's Decadal Survey ranked it a top priority for the 2030s. What makes LUVOIR so thrilling isn't just the science, it's the philosophical shift. For the first time, we wouldn't be guessing about exoplanets based on shadowy data. We'd have family portraits of other Earths. A single image of a cloudy, blue-white world with an oxygen-rich atmosphere could transform our place in the universe from solitary travelers to cosmic neighbors. And if LUVOIR found nothing, that silence might be even more profound, suggesting life, or at least complex life, is rarer than we dreamed. This isn't just another telescope. It's a mirror held up to the cosmos, ready to show us our reflection or reveal how utterly unique we might be. While still in the proposal stage, l'oeuvre represents the logical next step in a journey that began when Galileo first pointed a spyglass at the stars. 4 centuries later, we're on the verge of turning that spyglass around and looking back at ourselves from the outside. SpaceX's Starship isn't just another rocket, it's the cornerstone of Elon Musk's audacious plan to make humanity a multiplanetary species. This towering stainless steel behemoth, designed to carry 100 passengers or 100 tons of cargo, represents the most ambitious attempt yet to turn Mars from a distant dream into a tangible destination. Unlike traditional spacecraft built for one-off missions, Starship is engineered for reuse, refueling, and rapid turnaround, transforming interplanetary travel from a government-led endeavor into something resembling a transcontinental flight. The vision is as bold as the engineering. Musk envisions fleets of starships launching in tight synchronization during Mars's optimal launch windows, which occur every 26 months when Earth and Mars align. Each ship would carry the building blocks of civilization, pressurized habitats, solar arrays, life support systems, even 3D printers to manufacture structures from Martian soil. Early missions would focus on establishing propellant depots, using Mars's own carbon dioxide and water ice to synthesize rocket fuel for return trips. This in-situ resource utilization isn't just convenient, it's the linchpin of making the colony self-sustaining. Without it, every nail, liter of water, or watt of power would need to be hauled from Earth at astronomical cost. But the challenges are staggering. Mars's thin atmosphere offers little protection from cosmic radiation or solar storms, issues Starship's steel hull helps mitigate but doesn't solve. The planet's 1/3 Earth gravity could wreak havoc on human health over time, and no one knows how crops will fare in Martian soil laced with perchlorates. Even landing Starship safely requires unprecedented precision. Mars's wispy atmosphere makes parachutes useless, so the ship must execute a supersonic retropropulsion maneuver, basically flipping midair and firing engines to slow its descent, something never attempted at this scale. What sets Starship apart from past Mars concepts is its economic scalability. Traditional NASA missions might cost billions per astronaut. SpaceX aims to slash that figure by orders of magnitude through full reusability and mass production. The company's Boca Chica test site operates more like a factory than a research lab, iterating through prototypes at breakneck speed. Lessons from SpaceX's Falcon rockets, which transformed launch economics by landing boosters on drone ships, are being applied here, but with exponentially higher stakes. A single Starship launch could deploy more payload to Mars than all previous missions combined. The timeline is aggressive. Musk has floated dates as early as 2029 for an uncrewed test landing, with crewed missions potentially following in the early 2030s. Skeptics rightfully point out SpaceX's history of optimistic schedules, but the sheer pace of Starship development is undeniable. Since 2019, we've seen prototypes explode, hover, and eventually stick landings. The orbital test campaigns have pushed materials science to its limits, with heat shield tiles and Raptor engines undergoing brutal real-world testing no simulation could match. Beyond the tech lies a philosophical shift. Where Apollo was about proving superiority, Starship is about permanence. Its success wouldn't just mean flags and footprints, it would mean neighborhoods on Mars. The first settlers will likely be scientists and engineers, but Musk envisions artists, chefs, and teachers joining later waves. The legal and ethical frameworks for such a colony remain uncharted. Who governs Mars? How are resources allocated? These questions sound like sci-fi today, but may become urgent within decades. Perhaps the most transformative aspect is how Starship reframes humanity's relationship with risk. Spaceflight has always prioritized safety above all. but colonizing Mars will require a frontier mentality, accepting that some lives may be lost in pursuit of something greater. It's a calculus familiar to early polar explorers or settlers crossing oceans in wooden ships, yet alien to our modern risk-averse culture. Every explosion during testing, every setback, is part of the price for making interplanetary life routine. The ultimate test won't be technical, it'll be cultural. Can we sustain political will and funding across generations? Will people actually volunteer for a one-way trip to a frigid, airless world? And if they do, what happens when the first child is born under crimson Martian skies? Starship is more than a spacecraft. It's a mirror forcing us to confront who we are as a species and who we might become among the stars. While SpaceX grabs headlines with Martian ambitions, Jeff Bezos's Blue Origin is taking a different path, one that starts with the moon. Their Blue Moon lander isn't just another spacecraft. It's a versatile workhorse designed to deliver cargo, crew, and even the building blocks of a lunar future. Unlike NASA Artemis landers, which prioritize human missions, Blue Moon is engineered for flexibility, capable of supporting everything from scientific outposts to industrial operations. And its development reveals a broader vision, turning the moon into a hub for sustained activity, not just brief visits. The lander comes in two flavors, each tailored for specific roles. The cargo variant is a robotic powerhouse, able to deposit up to 3 metric tons of equipment on the lunar surface, enough to deploy habitats, power stations, or rovers ahead of human arrivals. But the real showstopper is the crewed version, a spacious capsule perched atop a descent stage, with windows offering astronauts panoramic views of the moon's stark landscapes. Both designs share a critical innovation: the use of liquid hydrogen as fuel, a choice that taps into another Blue Origin project harvesting ice from the moon's poles to produce propellant locally. This isn't just about landing, it's about staying. What sets Blue Moon apart is its precision. Using terrain relative navigation, the lander can touch down within meters of a target, avoiding boulders or craters that might jeopardize a mission. That's crucial for accessing the moon's most tantalizing real estate, permanently shadowed craters near the poles, where water ice lurks beneath the dust. Blue Origin has already demonstrated this tech with their experimental Silver Moon prototype, proving autonomous landings under simulated lunar conditions. The system is so accurate it could theoretically deliver multiple payloads to the same site, stacking components for a base like cosmic Lego bricks. Integration with other lunar projects gives Blue Moon added significance. Bezos envisions it as part of an ecosystem that includes the Orbital Reef Space Station, a commercial successor to the ISS and future orbital fuel depots. Picture this: a cargo lander ferries ice mining equipment to Shackleton Crater, where robots extract water and split it into hydrogen and oxygen. That fuel then powers crewed landers shuttling between the surface and orbital hubs, creating a sustainable loop that cuts Earth out of the supply chain. It's a vision that shifts lunar exploration from government-led flags and footprints to something resembling a railroad expansion, with Blue Moon as the locomotive. But the lander's true legacy might lie in its ripple effects. By proving reusable, precision landings at scale, Blue Origin could slash the cost of accessing the moon for everyone: NASA, academia, even rival companies. That democratization mirrors how Bezos's other company, Amazon, revolutionized logistics on Earth. And with NASA Artemis program hungry for commercial partners, Blue Moon is well positioned to become a cornerstone of America's lunar return. Contracts for cargo delivery or crew transport could turn Blue Origin from an ambitious startup into a pivotal player in the new space economy. Critics point out the project's slower pace compared to SpaceX's breakneck iterations. But Blue Origin's methodical approach, testing components like the B-7 lunar engine under brutal conditions, reflects a philosophy that prioritizes reliability over speed. After all, the moon isn't going anywhere, and building infrastructure for the long haul requires systems that won't fail when lives and billions of dollars are on the line. Looking ahead, Blue Moon represents more than hardware. It's a test case for how private enterprise might shape off-world expansion. Success could prove that companies, not just nations, can lead humanity's next chapter in space. And if its engines ever fire under Martian gravity, that would be a poetic twist, Bezos's lunar brainchild helping enable the very Martian future his rival champions. For now, though, Blue Moon's sights are set firmly on Earth's closest companion, turning science fiction into industrial reality, one precise landing at a time. China's space ambitions aren't just catching up, they're accelerating at a pace that's reshaping the global space race. At the forefront is the Tianwen program, a sweeping initiative that's already notched historic successes on Mars and is now setting its sights on even bolder goals. Tianwen-1, China's first independent interplanetary mission, stunned the world in 2021 when its Zhurong rover rolled onto the rusty plains of Utopia Planitia, making China only the second nation to land and operate a rover on the Red Planet. But Zhurong wasn't just a symbolic achievement, it was a showcase of precision engineering. While NASA Perseverance relied on a sky crane for its dramatic touchdown, Zhurong used a combination of parachutes, retrorockets, and airbags, a method reminiscent of earlier American and Soviet landers but executed with modern finesse. What's even more impressive is how quickly China is building on this success. While Zhurong studied Martian geology and climate, its parent orbiter has been busy mapping potential sites for Tianwen-3, a mission slated for the 2030s that aims to accomplish what NASA and ESA are attempting with Mars sample return, bringing pristine Martian soil back to Earth. But China's approach has a twist. Rather than the multi-spacecraft relay race planned by Western agencies, Tianwen-3 reportedly consolidates the process into a single launch, with an ascent vehicle pre-deployed on Mars to rendezvous with an orbiting return module. If successful, this streamlined architecture could give China the distinction of being the first nation to retrieve samples from another planet, a feat with enormous scientific and geopolitical weight. The Tianwen program's ambitions don't stop at Mars. Lunar missions are equally central to China's strategy, particularly the hunt for resources at the Moon's south pole, a region believed to harbor vast reserves of water ice. Following the triumphs of the Chang lunar probes, which included the first ever landing on the far side of the Moon, China's space agency has outlined plans for Chang 7 and -8. These missions will deploy rovers, landers, and even a mini-flying probe to study permanently shadowed craters, test 3D printing with lunar regolith, and lay the groundwork for the International Lunar Research Station, a proposed joint venture with Russia. This base, envisioned for the 2030s, could become a strategic foothold near water sources critical for future deep space missions. The geopolitical undercurrents here are impossible to ignore. While NASA champions the Artemis Accords, a framework for peaceful lunar exploration backed by Western allies China and Russia, have positioned their lunar station as an alternative open to other nations, particularly those outside traditional space power blocks. This isn't just about science, it's about influence. Control over lunar resources, especially water ice that can be split into hydrogen and oxygen for rocket fuel, could dictate who leads the next era of space exploration. China's methodical approach, landing on the far side of the Moon, retrieving lunar samples, and now targeting the South Pole, shows a long-term vision that balances prestige with practical gains. Yet challenges loom. Tianwen-3 sample return plan hinges on mastering orbital rendezvous around Mars, a feat only NASA has achieved so far. Lunar ambitions depend on sustaining political will and funding amid global economic headwinds. And while China's state-backed model allows for long-term planning, it lacks the competitive dynamism driving private sector innovations in the US and Europe. Still, the Tianwen program's blend of ambition and execution makes one thing clear. The future of space exploration won't be a solo endeavor. It'll be a high-stakes interplay of science, strategy, and soft power, with China now a central player at the table. Even as Louvre promises to revolutionize our search for Earth-like worlds, NASA is already paving the way for its spiritual successor, the Habitable Worlds Observatory. This next-generation space telescope isn't just another eye on the cosmos. It's a precision instrument engineered for one extraordinary purpose: to detect signs of life on planets orbiting distant stars. Where its predecessors inferred habitability from orbital data or atmospheric chemistry, the Habitable Worlds Observatory will bring these alien environments into sharp focus, analyzing their light for the faintest whispers of biological activity. The telescope's design blends cutting-edge optics with brute force sensitivity. Its primary mirror, spanning at least 4 meters, will gather light with unprecedented clarity, while advanced coronagraphs block out the overwhelming glare of host stars like spotting a firefly next to a searchlight. But the real magic happens in its spectrographs, instruments so refined they can tease apart the chemical fingerprints of exoplanet atmospheres from light years away. Imagine identifying oxygen, methane, or even industrial pollutants like chlorofluorocarbons in the air of another world. These wouldn't just hint at life, they could reveal whether that life has evolved into something more complex. Uniquely, the observatory will focus exclusively on habitable zone planets around Sun-like stars, filtering out cosmic noise to study only the most promising candidates. Unlike broader survey telescopes, it's a cosmic detective trained to scrutinize targets pre-vetted by missions like TESS and Plato. Once locked onto a planet, it could monitor seasonal changes in vegetation cover, detect ocean glints, or spot the infrared signatures of cities lighting up the night. Some concepts even include a starshade, a separate spacecraft flying tens of thousands of kilometers ahead to create an artificial eclipse, darkening the star further and unveiling planetary details no telescope could see alone. The technological leaps required are staggering. The mirror must be polished to atomic-level smoothness to prevent light scattering. The coronagraph demands stability beyond anything currently achievable, compensating for vibrations equivalent to a fraction of a hydrogen atom's width. And the entire system needs to operate at cryogenic temperatures to avoid its own heat drowning out faint planetary signals. Yet early prototypes like the coronagraph on NASA and Nancy Grace Roman Space Telescope are proving these feats possible. The Roman's tests will serve as a dress rehearsal for the observatory's more ambitious systems, working out kinks before the main act. What sets this mission apart is its singular focus on biosignatures. While Louvre and Hubble offered panoramic views of the universe, the Habitable Worlds Observatory is a sniper scope dialed in on one question: are we alone? Its findings could range from mundane detecting simple microbial byproducts to earth-shaking, like spotting the spectral signature of chlorophyll on a world 20 light-years away. The telescope might even stumble upon technosignatures, evidence not just of life but of civilizations altering their environment in ways we'd recognize. Timing is everything. Slated for launch in the 2040s, the observatory will arrive just as astronomers compile their first catalog of potentially habitable exoplanets. It won't just study these worlds, it'll rank them by similarity to Earth, prioritizing targets for future interstellar probes. Some scientists speculated could identify a dozen planets with strong biosignatures within its first decade, fundamentally altering our understanding of life's cosmic prevalence. Philosophically, the telescope bridges two eras, one where habitable worlds were theoretical, and another where they're tangible places we might one day explore. Its data could finally answer whether life is a statistical inevitability or a freak accident, and whether intelligence follows predictable paths or blossoms in forms we can't yet fathom. The Habitable Worlds Observatory isn't just a machine, it's the lens through which humanity may first glimpse its cosmic kin. The concept sounds like something ripped from the pages of a futuristic novel, vast solar arrays floating in space, harvesting endless sunlight and beaming clean energy back to Earth. But what was once pure science fiction is now edging toward reality, with international teams racing to make space-based solar power a viable piece of our energy future. At the forefront is Caltech's Space Solar Power Project, which recently stunned scientists by successfully transmitting detectable power from orbit for the first time in history. Their prototype, launched in early 2023, unfurled lightweight solar panels no thicker than a notebook, then used microwave transmitters to send energy across a short distance in space. While the amount of power was tiny enough to light a single LED, the implications were enormous. It proved that wireless energy transfer in space isn't just theoretical, it's technically achievable. Japan's ambitions take the idea even further. Their government, in partnership with Mitsubishi and JAXA, plans to conduct the first full-scale orbital demonstration by 2025. Unlike Caltech's small-scale test, Japan's design involves a constellation of mirror-like satellites concentrating sunlight onto photovoltaic panels, then converting that energy into microwaves beamed to receiving stations on Earth. These rectifying antennas would transform the microwaves back into electricity and feed it into the grid. Early calculations suggest a single-kilometer scale array in geostationary orbit could generate roughly 1 gigawatt of power equivalent to a nuclear reactor, with near 24/7 availability, unaffected by clouds or nighttime. The potential advantages over terrestrial renewables are staggering. Earth-based solar farms lose half their potential output to night and weather, while orbiting arrays bask in unfiltered sunlight nearly continuously. Space offers another critical edge: no atmosphere to scatter or absorb solar rays, meaning photovoltaic cells could operate at peak efficiency. And unlike wind or ground-based solar, space solar doesn't compete for precious land area, a growing concern as populations expand and ecosystems falter. For energy-hungry nations with limited space like Japan or Singapore, this could be transformative, yet the challenges are as vast as the promise. Beaming gigawatts of power through the atmosphere raises safety questions. Could misaligned microwave beams accidentally fry passing aircraft or birds? Engineers insist the energy density would be too diffuse to harm humans or wildlife, but public perception remains a hurdle. Then there's the monumental cost of launching and assembling kilometer-scale structures in orbit. Current estimates suggest space solar would need launch prices to plummet below $200 per kilogram to compete with terrestrial alternatives, though advances in reusable rockets and in-orbit assembly could help bridge the gap. Material science presents another obstacle. Solar panels in space face relentless degradation from cosmic radiation and micrometeoroid impacts. New ultra-lightweight, radiation-resistant designs are in development, including Caltech's modular tiles that can still function even if individual units fail. Perhaps the most underrated hurdle is infrastructure. Countries would need sprawling rectangular farms covering dozens of square kilometers to capture the beamed energy. Placing these in remote areas could minimize land use conflicts, but transmission losses over long distances might negate the benefits. Critics argue the money would be better spent improving Earth-based renewables and grid storage. After all, why gamble billions on unproven orbital tech when wind and solar keep getting cheaper? Proponents counter that space solar isn't meant to replace terrestrial solutions, but to complement them, providing baseload power that stabilizes grids increasingly reliant on intermittent sources. There's also the strategic angle. Nations mastering this technology could gain energy independence and export clean power globally, reshaping geopolitical dynamics. The coming decade will be decisive. Beyond Caltech and Japan, the European Space Agency has outlined its Solaris initiative, while China reportedly has covert projects underway. Private ventures like SpaceX's Starship could provide the heavy lift capability needed to make orbital arrays economically viable. Whether space solar becomes a cornerstone of our energy mix or remains a niche solution depends on solving those engineering and economic puzzles. But for the first time, it's no longer a question of if, but when and how. The dream of limitless clean energy from above is finally within our grasp, waiting just beyond the edge of the atmosphere, far beyond the orbits of planets where the sun's influence fades into the void. An invisible frontier shapes our cosmic neighborhood, the heliosphere. This colossal bubble, carved by the solar wind's relentless outflow, shields Earth from 70% of the galaxy's harsh cosmic rays, but its exact workings remain one of space science's great puzzles. Enter NASA Interstellar Mapping and Acceleration Probe, or IMAP, a mission designed not just to study this mysterious boundary, but to decode the very forces that could make or break humanity's dreams of deep space exploration. Scheduled for launch in 2025, IMAP will park itself at Lagrange Point 1, a gravitational sweet spot a million miles sunward of Earth. From this vantage, its 10 instruments will perform a delicate ballet of detection, capturing particles that ricochet inward from the heliosphere's edge. These aren't just any particles, they're energetic neutral atoms, ghostly messengers formed when solar wind particles collide with interstellar material at the boundary. By mapping their paths, IMAP will effectively trace the heliosphere's contours in 3D, revealing its shape and structure like a medical scan for our solar system. But the mission's stakes go far beyond cartography. Cosmic rays, high-energy particles from supernova and black holes, pose one of the greatest threats to interplanetary travel. Without Earth's magnetic field and atmosphere as armor, astronauts venturing to Mars would face radiation levels equivalent to a CT scan every 5 days. IMAP cosmic ray detectors will study how these particles are filtered or accelerated at the heliosphere's edge, providing critical data for shielding future spacecraft. Some theories suggest the boundary acts as a chaotic particle accelerator, boosting certain cosmic rays to dangerous energies, a phenomenon IMAP could confirm or debunk. The probe's most revolutionary tool might be its coherent radio frequency instrument, designed to track microscopic dust grains from interstellar space. These tiny travelers, pushed by starlight pressure, carry chemical signatures of distant star-forming regions. Analyzing their composition could reveal how elements essential for life, carbon, oxygen, iron, are distributed across the galaxy. It's cosmic forensics, with IMAP as the detective piecing together our solar system's connection to the wider Milky Way. What makes IMAP truly groundbreaking is its dual role as both explorer and protector. By modeling how the heliosphere modulates cosmic radiation, scientists could develop early warning systems for solar storms or design magnetic deflectors mimicking Earth's natural shielding. The mission even ties into interstellar travel dreams. Understanding this boundary is crucial for any future probe venturing beyond the sun's influence, like the proposed interstellar successors to Voyager. Unlike missions focused on single discoveries, IMAP operates like a cosmic weather station, streaming real-time data about the ever-shifting frontier around us. Its findings might not make flashy headlines, but for astronauts on the Moon or Mars decades from now, this knowledge could mean the difference between life and death. The heliosphere isn't just a scientific curiosity, it's our first line of defense against the galaxy's fury, and IMAP is about to show us how that shield really works. As we push farther into space, missions like this remind us that exploration isn't just about reaching new places. It's about understanding the invisible forces that will let us survive the journey. The data streaming back from IMAP won't just fill textbooks. It might one day protect colonists on distant worlds, proving yet again that the quietest science often speaks loudest when humanity takes its next great leap. Imagine a tiny, resilient microbe hiding in the rusty soil of Mars, proof that life isn't unique to Earth. That's the monumental possibility driving the next generation of Martian explorers, not rovers or rock collectors, but fully equipped astrobiology labs designed to hunt for life in real time on location. Future missions could deploy self-contained laboratories packed with tools straight out of a sci-fi novel: miniature DNA sequencers, fluorescent microscopes that glow in the presence of organic molecules, even microfluidic chips that process soil samples with the precision of a forensic team. These wouldn't just analyze rocks, they'd perform the most consequential experiments in human history, answering a question that's haunted us for centuries: are we alone in the universe? The challenges of searching for Martian microbes are staggering. Earth bacteria can hitchhike on spacecraft, contaminating samples with false positives. Martian life, if it exists, might not use DNA as we know it, or might thrive in ways so alien that our tests overlook it entirely. That's why next-gen labs are being designed with radical flexibility. One concept, the Search for Extraterrestrial Genomes (SEC) instrument, doesn't assume Martian life shares our biochemistry. Instead, it looks for any genetic material, even exotic nucleotides bound by unfamiliar rules, by injecting soil samples with fluorescent dyes that latch onto double helix structures, no matter their composition. Another approach pioneered by NASA Jet Propulsion Lab uses lab-on-a-chip technology, credit card-sized devices that mix samples with chemical probes, hunting for amino acid patterns statistically improbable in non-living systems. But the real game-changer might be hybridization, combining multiple techniques to cross-verify results. Picture a rover's robotic arm scooping soil into a compartment where lasers vaporize it, releasing gases for mass spectrometry. Simultaneously, a fraction of the sample gets piped into a microbe detection chamber infused with dyes that glow in the presence of cellular membranes. Any hits trigger a third test: exposure to nutrient broths designed to make dormant microbes metabolize and multiply. This layered approach reduces the risk of false negatives, ensuring we don't miss life just because it doesn't match our expectations. The stakes couldn't be higher. A confirmed detection would rewrite biology, proving life can emerge independently in multiple places. But even a definitive negative result would be profound, suggesting Earth's biodiversity might be a cosmic fluke. Future labs won't just search, they'll contextualize. Instruments like Raman spectrometers could map the mineral surroundings of potential microbes, revealing whether they cluster near ancient hot springs or subterranean brines. Isotope analyzers might catch them in the act of respiration, digesting Martian perchlorates the way Earth bacteria consume oxygen. Every data point would paint a clearer picture of how life adapts or fails to on other worlds. The tech is advancing faster than many realize. Private labs have already shrunk DNA sequencers to the size of USB drives, while AI-powered microscopes can now detect bacterial movements invisible to human eyes. Adapting these tools for Mars requires hardening them against radiation and sub-zero cold, but prototypes are already undergoing trials in Earth's most Mars-like environments, from Chile's Atacama Desert to Antarctica's dry valleys. The European Space Agency's ExoMars rover, though delayed, carries a drill capable of reaching 2 meters down where cosmic rays haven't sterilized the soil, and a suite of instruments fine-tuned to spot biosignatures in clay layers that might have sheltered ancient organisms. What makes these labs revolutionary isn't just their science, it's their potential to shift exploration from passive observation to active interrogation. Instead of waiting years for samples to return to Earth, they'd conduct experiments on site, adapting protocols if initial results intrigue. A detection of complex organics might trigger a follow-up search for chiral molecules, which often hint at biological origins. Unusual mineral deposits could prompt a drill to go deeper, chasing chemical gradients that mimic Earth's deep-sea vents where life thrives without sunlight. The philosophical implications are dizzying. Finding even a single microbe on Mars would suggest the universe teems with life, but its biological quirks could reveal whether we share a common ancestor, perhaps scattered by asteroid impacts, or if life arose separately following different rules. Future labs might settle the debate by sequencing Martian genes if they exist and comparing them to Earth's tree of life. A match would hint at planetary cross-contamination. A radical divergence could mean biology is more inventive than we ever imagined. With every mission, we're not just building better instruments, we're refining the very definition of life. The next wave of Martian explorers won't just carry cameras and drills, they'll pack entire laboratories designed to ask the universe its deepest question. And somewhere in the red dust, the answer might already be waiting. From unraveling the origins of life on icy moons to establishing human footholds on Mars, these 20 missions represent more than just scientific curiosity. They're the building blocks of humanity's future as a spacefaring civilization. Think about it, in just a few decades, we could be analyzing Martian soil for ancient fossils, flying drones through Titan's methane skies, or receiving the first high-resolution images of an Earth-like exoplanet. Each mission carries the potential to redefine our place in the cosmos, whether by answering age-old questions about alien life or laying the practical groundwork for interplanetary cities. Consider the ripple effects of these endeavors. Missions like Europa Clipper and Dragonfly aren't just exploring new worlds, they're teaching us how life might arise in environments once deemed inhospitable. Breakthroughs in propulsion, from SpaceX's Starship to breakthrough Starshot's laser sails, could slash travel times across the solar system and beyond. Even seemingly niche projects like a map and space-based solar power have Earth-shaking implications, protecting astronauts from cosmic radiation or beaming limitless clean energy to our planet. The common thread: these aren't isolated experiments, they're interconnected steps toward making the cosmos accessible, understandable, and ultimately habitable. What's most exhilarating is how quickly fiction is becoming reality. The Lunar Gateway, once a sketch in engineers' notebooks, will soon orbit the Moon as a staging post for deep space voyages. The Habitable Worlds Observatory, still in planning, might capture the first definitive evidence of life beyond Earth within our lifetimes. And let's not forget the unsung trailblazers, missions like Veritas and Psyche, probing planetary evolution in ways that could reveal Earth's distant past or possible future. Every launch, every dataset, every rover rolling onto alien soil adds another piece to the grand puzzle of our cosmic neighborhood. Now it's your turn to join the conversation. Which mission sparks your imagination? Are you captivated by the hunt for extraterrestrial microbes, or do visions of Martian cities quicken your pulse? Drop your thoughts in the comments. We'd love to hear which frontier speaks to you. And if you're as passionate about humanity's next chapter as we are, hit subscribe for all the latest updates on these groundbreaking ventures. The countdown to tomorrow's discoveries has already begun, and the best seats in the house are right here. Let's explore the future together.